This program is brought to you by Stanford University. Please visit us at stanford.edu.
I want to work out a few examples, 2 examples, 3 examples, not in particular order of ascending complexity. The first one is going to be very simple, the next one is going to be more complicated, and the third one is going to be even simpler than the first one. I have my reasons. But the first 2 examples are to show you how much easier it is to use Lagrange's equations and to use the formal structure of classical mechanics that we've learned up till now, the mindless set of mechanical rules, than to actually sit there and try to use F equals ma for all the parts of a system and juggle all the different parts of the system and use the fact that the forces on one are equal and opposite to the forces on the other. That can often be just incredibly complicated, whereas working out the Lagrangian is very simple usually. Now there's a simple mathematical reason. When you work out F equals ma, a is the second derivative with respect to time of something. That means you have to start calculating second derivatives. You have to start calculating accelerations. And that's often complicated, much more complicated than calculating velocities, which are just first derivatives. If you can calculate the velocity of a system, you can calculate its kinetic energy very easily, 1/2 mv squared. If you've calculated its kinetic energy and also its potential energy, you know the Lagrangian, and from that, like a mechanical fool, you can sit down and calculate the equations of motion. When you know the equations of motion, you can put them on a computer and grind out trajectories. Calculating accelerations is harder, typically, than what I have in mind, of course, when I say calculating accelerations, is I have in mind where you have some complicated set of coordinates, where your coordinates are not simply rectangular coordinates, some angles, some other kinds of things, and out of this you have to calculate components of acceleration. That's often much, much more complicated than just calculating the kinetic energy. Let me take the first example I'm going to study is the simple pendulum. Then we're going to do a more complicated kind of pendulum. The simple pendulum is simple enough that with a little bit of thought and a little bit of cleverness, you can figure out how the forces on the pendulum bob and then use F equals ma. Okay? The compound pendulum we're going to do is far more complicated and would boggle the mind of anybody trying to use F equals ma. But both of them are relatively simple, not too hard to work out if you know Lagrangian, if you know your Lagrangians. All right, so let's start with the simple pendulum. Simple pendulum is just a weight hanging, whoops, I don't think I like the way I drew it. Let's draw it slightly different. Let's draw it hanging at an angle. All right, so it's connected to the ceiling. It hangs at an angle. I assume that it's connected, the pendulum bob has mass m. It's connected by a rigid rod to a pivot at the ceiling. And we'll take the rigid rod to be so light that its mass is not important. Right, so all of the mass is concentrated at the end of the pendulum. And the angle relative to the vertical is called theta. All right. There are 2 features of the theory. There are 2 things in the Lagrangian, potential energy and kinetic energy. Potential energy is proportional to the height above some particular point. And of course, the height will depend on the angle. As the pendulum swings, the height will change, and as the height changes, the potential energy changes. And then there's kinetic energy, and kinetic energy is just related to the velocity of the pendulum bob. All right, let's first, we need to specify what the length of the pendulum is. This is the pendulum length doesn't change. It's just a constant in this problem. Let's call it r. R is just a number, 1 meter or 1.5 meters or 6 inches or whatever. It's not going to change. The mass doesn't change. The only thing that changes in this problem is theta. There's the only thing which changes with time is theta. And we want to work out its equations of motion. All right, what's the horizontal distance here that's related to r, and it's related to theta. Thank you. R sine theta. All right, since you're so smart, what's the vertical one? R cosine theta. That's this distance here. Let's calculate the components, the x and y components of the velocity of the mass. All right? They're just the time derivatives of the vertical and horizontal components. Right? Okay, so what is the, oh, incidentally, if we count, this is fine. Yeah, let's calculate the x component of velocity. The x component of velocity is just the time derivative of r sine theta. R doesn't change, only sine theta changes. So the x component of velocity, all right, v is equal. Now, there's going to be two components to it. The first component is the x component. It's r times the derivative of sine theta, that's cosine theta, times the time derivative of theta. If I want to know the time derivative of sine theta, I differentiate with respect to theta, and then I multiply by the time derivative of theta. So that's r cosine theta times theta dot. That's the x component of the velocity. The y component of the velocity, I'm counting components downward, I guess. I count distance downward as positive in this picture here. So the vertical component of the velocity is the time derivative of r cosine theta, and that's r minus r sine of theta times theta dot. Why minus? Because the derivative of cosine is minus sine. So these are the two components of the velocity of the pendulum bob. And now if we want the kinetic energy, we just have to write 1/2 mv squared. So the kinetic energy, T, is just 1/2 the mass times the sums of the squares of the components of the velocity, Vx squared plus Vy squared. Okay? These are components of the velocity in two perpendicular directions. The total velocity, or the total speed, is the sums of the squares. And what is that? That's going to be r squared, theta dot squared, times cosine theta squared plus sine of theta squared. All right. Each component we're given r squared and a theta dot squared in the square of the velocity. And then one of them has cosine squared, the other has sine squared. But what is cosine squared plus sine squared? It's just 1. So the kinetic energy is just 1/2 the mass times r squared times theta dot squared. We can forget cosine squared plus sine squared. It's just 1. That's the kinetic energy of the pendulum bob. What about its potential energy? The potential energy is simply the height above some particular point. We could take that point to be the ceiling. Pendulum can swing around. Let's take the potential energy to be 0. Well, let's see. Yeah, let's take the potential energy to be 0 when theta is, when the pendulum is absolutely horizontal. The point is, of course, it doesn't matter at what point you choose the potential energy to be 0. Only differences of potential energy are important. And so the height of the pendulum is minus because it's hanging down, minus r cosine of theta. When theta is 0, then the height is minus r. When theta is pi, it's up on the top, then the height is plus r cosine theta, or just plus r. So the minus sign is there to keep track of the fact that when theta is 0, the energy is minimum. It's down at the bottom. That's not u, that's just the height of the pendulum relative to the pivot. What's the potential energy of a particle in a gravitational field? mg times the height. So we have to multiply this by minus m times the acceleration of gravity. This is the potential energy. Let's write the Lagrangian. The Lagrangian is just m over 2 r squared theta dot squared minus the potential energy. Minus the potential energy. The potential energy itself has a minus in front of it, so that means we should add mg r cosine of theta. Again, why plus? Because we want minus the potential energy in the Lagrangian, and the potential energy has a minus sign. Two minus signs make a plus sign. That's a lot easier than figuring out the acceleration and using F equals ma for the two components of motion and then juggling them together. The Lagrangian, all we really needed to do was to calculate the velocity as a function of theta dot, and here it is. All right, what about the equations of motion? Let's write down the equations of motion. First of all, we take the canonical momentum conjugate to theta, that's pi sub theta. That's equal to the derivative of the Lagrangian with respect to theta dot. That's mr squared theta dot. It's actually the angular momentum, but we don't even need to call it that. We just call it mr squared theta dot. And then the equation of motion is that the time derivative of this, d by dt, of mr squared theta dot, that's the usual d by dt of the derivative of the Lagrangian with respect to the velocity, that's equal to the derivative of the Lagrangian with respect to theta. What is that? That's minus mg r sine of theta. Or we can just write this, we can cancel out the masses, of course, and then we can write this as r squared. Remember, r is just a number, it doesn't vary in the problem, times theta double dot, the angular acceleration, is equal to minus gr times sine theta. This can be stuck on a computer. Right? We either take it as a differential equation to solve, or we break up the time axis into lots of little intervals and do it numerically. I'm going to assume in this course that every equation that we could write down has a solution, and that you know how to find the solution, if not by nothing else, by setting it up on a computer to simulate simple differential equations like this. And it's fun to do it. If you haven't done it, do it for some simple equations of this type. And this simply tells you the acceleration as a function of the angle. So it's a usual kind of F equals ma type equation. While we're at it, let's just calculate the energy. We know what the energy should be. The energy should just be the kinetic energy plus the potential energy. The Lagrangian is kinetic energy minus potential energy. But let's do it by the mindless method. The mindless method says that the Hamiltonian is equal to the momentum, what did I call it? Pi sub theta times theta dot. This is pi times q dot. All right, we worked that out last time. Minus L. What I'm writing is pi sub I q sub I dot minus L. That's where you sum over I. But there's only one coordinate in this problem, so that's it. Pi sub theta, what's pi sub theta? Pi sub theta is mr squared theta dot. So this becomes mr squared theta dot times another theta dot squared. That's pi theta dot. Minus the Lagrangian, so it's minus mr squared over 2 theta dot squared minus mg r cosine theta. These two things constitute minus L. Okay, so this is easy. mr squared theta dot squared, m over 2r squared theta dot squared. This cancels half of this and just turns this into plus. That's the energy, Hamiltonian, or equivalently the energy. That's it. Okay. It is the kinetic energy plus the potential energy. Don't get fooled by this minus sign here. The potential energy had a minus sign in it.
Why we would kind of expect pi I q dot r, q dot I to be equal to 2t.
Oh, it's almost always equal to 2t. Yeah, doesn't have to be, but it's often 2t. Certainly, if the kinetic energy is of the form 1/2 mv squared, then it's always going to be that way.
So far, I've only seen examples where that was the case.
We can concoct some in which it's not the case, and I'll remind me. But for the simple examples, it's usually the case. But don't trust it. Don't trust a thing like that. You work out each example separately. All right, that's the energy. How does the pendulum move? Well, I'm not going to solve the equations of motion, but of course we know how it moves. We have a pretty good idea. If the energy is, all right, let's first of all notice what's the difference of energy at the bottom of the orbit and the top. The difference of the energy at the top, we would have mg times cosine of pi, or minus that. So at the top, the energy is plus mgr, and at the bottom it's minus mgr. All right? So it takes some energy to get to the top. From the bottom to the top, you have to pay a price twice mgr. Let's imagine starting the pendulum at the bottom here with a certain velocity. We give it a poke to give it some velocity. If the velocity is not enough, if the kinetic energy at the bottom is not enough to overcome the necessary energy to get to the top, then of course what will happen is the pendulum will swing up, run out of kinetic energy. It has converted some kinetic energy to potential energy, but it didn't have enough to get to the top, and so it'll start back. It'll swing to the other side, and it will just endlessly oscillate back and forth symmetrically on both sides. That's intuitively clear, and it actually is a feature of the equations. Just endless oscillation, almost like a harmonic oscillator, which is a system we're going to study shortly, but a little more complicated. Yeah. What's that? No, theta is pi at the top. Pi is 180 degrees. Oh, no, oh, I see what you mean. No, I'm sorry. Okay. The top doesn't mean when it's, I'm imagining, good. I'm imagining a pivot point, and the pendulum swings around 360 degrees around the pivot point. So the top means up here. Good point. Okay.
Well, you said ceiling a couple times.
Yeah, well. Right. Yes. No, that's right. What I meant by the top of the orbit was when the pendulum is vertically upright, okay, and above the ceiling. Okay. What if it does have enough energy to climb to the top? If it has enough kinetic energy at the bottom so that by the time it gets to the top, it still has a little bit of kinetic energy left over, in other words, if its kinetic energy to begin with is a little bit bigger than 2 mgr, then it will have kinetic energy to spare when it gets to the top, and it will just keep going, and it'll cycle around, going faster at the bottom, slowing down, going over the top, and just endlessly round and round and round and round. So there are two kinds of orbits, two kinds of motions, really strictly speaking three. There's oscillation back and forth, and there's, what shall we call it? I don't know. Yeah. Kind of rotating motion to the left and a rotating motion to the right. Of course, you can ask, what happens if it has exactly enough energy to get to the top? Well, then it'll just go to the top and sit at the top. But that's highly fine-tuned and not the sort of thing you're likely to encounter. So we'll ignore that possibility. There's nothing wrong with it. You just go up to the top and just get there barely, and you stop. Okay, that's the basic pendulum. And as I said, my main reason for, well, two reasons for illustrating it. The first is just to show you that it's easier to calculate using Lagrangians than it would be to F equals ma for a system as complicated as this. But really, I want to show you another system, which is the double pendulum. The double pendulum is a far more complicated system. It has very, very complicated motions. Its motions are chaotic. We haven't learned what chaos means yet. We will. But its motions are chaotic and truly baffling if you watch the double pendulum. And if you were to try to study it by using just F equals ma without knowing the Lagrangian formulation of it, you would spend hours working out its equation of motion. It's too complicated it would certainly be too complicated for me to do on the blackboard. But if you know how to calculate Lagrangians, it's just mechanical. Here's what the double pendulum is. Again, a pivot point. Pendulum hangs from it. Same deal as before. It has length r and mass m. I won't bother writing its mass. But then connected to this pendulum, there's another one. I'll also, for simplicity, give it radius r. And to keep it simple, I'll give it the same mass as the first one. Okay? It's also in a gravitational field. This one swings while the first one swings, and the whole thing is a really complicated mechanical system. And it's even complicated just to work out its equations of motion, except, yes?
Something on the same plane?
Yeah, in the same plane. Now, we could do it more generally. No good big problem about doing it more generally. But I'll take the case where they're in the same plane. You could have asked that up there, too. Is it a planar pendulum, or is it a pendulum that can swing out in all directions? I chose to do the planar pendulum. It might be fun to work out the equations for the full three-dimensional pendulum, which can swing out of the blackboard, but I won't do that here. In fact, it's easy enough. We could do it here, but we won't. All right, let's give it some coordinates. The first thing that you do when you see a problem like this is to define some coordinates. All right? A little bit of experience will teach you what the best choice of coordinates is, and if you don't choose the best choice, that's okay too. I mean, just pick a set of coordinates, and a set of coordinates means those things which determine the position of the system, a minimal number of objects which determine the position of the object. All right, the first coordinate is, of course, theta, the angle that the first pendulum makes relative to the vertical. Now you kind of have a choice. You could take, for the second pendulum, you could take the angle that the second pendulum makes with respect to the location of the first pendulum. We could call it phi. Or we could take the angle of the second pendulum with respect to the vertical. 6 of one, half a dozen of the other. I chose in my notes to use the angle relative to the vertical. All right. So this I call phi. And that's it. If you know theta and you know phi, you know the location of the pendulum completely. Now we need to calculate the kinetic and potential energy. So let's first calculate the kinetic energy of the first bob over here. Okay. It's exactly the same, no difference. The calculation is identical. Once again, this is r sine theta, and so forth. I can just write down the answer for the first piece of it. It's just 1/2 m theta, 1/2 m r squared theta dot squared. That's the kinetic energy of the first bob. But what about the second one? Well, the second one is moving for two reasons. One of them is that the first bob is moving, and if the first bob is moving, even if the angle phi were not changing, the second bob would move. So we have to add two velocities together to get the velocity, the components of velocity of the second bob. To get the the components of velocity of the second bob are the sum of the velocity as if this was standing still plus the component of motion of the first bob. I'll write down the answer and you'll see why it is. I think you won't have much trouble seeing why it is. The velocity of the second bob, let's give it some components. Here it is, velocity of the second bob. It has two components.
V3 plus V interacting.
Sorry?
V3 plus V interacting.
V3 plus free. Well, I don't know why you call it interacting, but you can. You can call it whatever you want.
Alluding to the
Oh, the fact that it's attached to this one. Yeah. We can also call these things whatever we want. I call him Bob. You could call him Herman. It doesn't matter. But we could call him Bob and this one Herman. I like that. This one's Bob. This one's Herman. OK, so here's Bob's kinetic energy. And Herman's kinetic energy has, or Herman's velocity, has two components. Of course, has two components, but each component itself consists of two parts. All right? So the x component of motion, the x component of Herman's velocity, will consist of the x component of Bob's velocity. That is, where is it? R cosine theta times theta dot. And then the component of Herman relative to Bob. Pretend Bob is standing still. What would be the x component of Herman's motion? Well, it'll be exactly the same as Bob's, except instead of theta, put phi. If Bob was standing still and Herman were oscillating or swinging, then we would add to this plus r cosine of phi times phi dot. That's the x component of motion. Two pieces to it. One associated with the fact that Bob moves, that's this one, and the other associated with the fact that Herman moves relative to Bob. Now what about the y component? Exactly the same thing. Bob has some y motion, and Herman has some y motion relative to Bob. Exactly the same. So this is the x component, comma, and the y component would be r minus r sine theta, theta dot, minus r sine of phi times phi dot. Are there any questions about what I've written down? All I've done was treat Herman as if he were a pendulum of exactly the same kind, substituting the angle phi wherever I saw theta in the first calculation. Right. Good. Now we can calculate the kinetic energy. We know the components. Here's the kinetic energy of Bob. Here's the components of velocity of Herman. Let's calculate Herman's kinetic energy. Let's do it over here. Herman's kinetic energy is 1/2 m, same velocity, sorry, same mass. Now, we have to square this and add it to the square of this. This is the x component, here's the y component. What do we get? Let's see if we can examine it and see what we get. we're going to get r squared cosine theta squared theta dot squared when we square the x component. We'll square this, and we'll add to it the square of the y component. So we're going to get this squared plus this squared. What does that give us? That gives us r squared cosine squared plus sine squared, that's 1, times theta dot squared. Okay, so that's just going to be 1/2 m r squared theta dot squared. All I've done is said that when I square Vx and I square Vy and add them together, it gives me a term with a cosine squared and a term with a sine squared. All right? Those add together to just give theta dot squared. Then we have the same thing over here. It's going to do exactly the same thing, plus 1/2 m r squared phi dot squared. That's coming from the square of this piece plus the square of this piece. Cosine phi squared plus sine phi squared also adds to 1. What have I left out? I've left out the cross terms. This times this, and this times this. Okay? Okay, so let's add them in. We have plus, of course, well, it's 1/2 m again, 1/2 m r squared times 2. There's always a 2. When a plus b squared has 2ab. So there's a 2. That'll eat up this 2 in the denominator. It'll give us a theta dot times a phi dot. Ooh, that's something new. Theta dot times phi dot. This is the first time we've seen velocities coming in multiplying each other. So it's theta dot times phi dot. There's m r squared, and then there's cosine theta cosine of phi. But there's also a term from the cross term from Vy, from the y component. That's going to be exactly the same, except that it will have sine theta times sine phi instead of cosine. So there's plus sine theta sine phi. This looks to me like the kinetic energy of Hermann, which I now add to the kinetic energy of Bob to get the total kinetic energy. That just takes this factor of a half away. Removes the factor of a half, just doubles this term involving theta dot squared. The fact that it just doubled it was because of a special choice of the fact that I took the same radius vector, the same radius here, and the same mass. In general, it would just do something else. It wouldn't just double it. But I chose the numbers simply so that it would just do something nice and simple, and that's it. Now, what about cosine theta times cosine phi plus sine theta times sine phi? Anybody recognize that? Yes? So what is it? Cosine of theta minus phi. Okay, this is cosine of theta minus phi. Cosine theta minus phi. I hate putting brackets inside parentheses. I'll just put an underline here to indicate that these are grouped together. Oh, no, we can, I guess we don't know. We can spare a parentheses there. That's it. Is it surprising that it's cosine of theta minus phi? Not really, and I'll tell you why. Supposing we didn't have the gravitational field here altogether. Supposing there was no preferred direction. The preferred direction in this problem is the vertical direction due to the gravitational field. If there was no preferred direction, the problem would have a symmetry. The symmetry would be rotation symmetry, where you rotate both theta and phi simultaneously. If you just rotated the whole thing, and so you kind of expect that the Lagrangian should not change if you added to theta and phi the same angle. That would just be rotating everything. Now, that is more or less obvious when you think about it. If you just took the whole configuration and rotated it, the Lagrangian shouldn't change. And that's what tells you that only angle differences should come in here. An angle difference doesn't change if you add to both theta and phi. The sum of the angles would change. If I added 2 degrees to theta and I added 2 degrees to phi, then theta plus phi would get added 4 degrees. But theta minus phi wouldn't change at all. So there's a symmetry to this problem in the absence of the potential energy. If we don't have a potential energy associated with the gravitational field of the Earth, then the problem has a symmetry. And the symmetry, we'll work it out later. We're going to work out the conserved quantity that's associated with it. It is, of course, some form of angular momentum. But before we do that, let's work out the potential energy.
Question.
Yes?
I lost track of why you raised up in half.
Oh, yes, good. All right, so from Hermann, we had a 1/2 mg, sorry, 1/2. Bob and Hermann conspired to get rid of the half.
Lost the 1/2 in the final equation.
What's that?
There's a 1/2 MR, the first term is 1/2.
No. No, 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 no.
You brought it over from the other one?
Yeah. I added Bob together with Hermann. Hermann also had an mr squared theta dot squared. And so, good. Good. So that's the kinetic energy. What about the potential energy? Well, this is T, kinetic energy. Potential energy, that's exactly the same as it was for the single pendulum, except we have to add up a contribution for both the Bobs, for Bob and Hermann, excuse me. All right. For Bob, it's minus mg cosine theta. And then for Hermann, it's another minus mg cosine of phi. Cosine? Yeah, cosine of phi. R, thank you. mg r cosine theta. Right, so the total Lagrangian, we now have the Lagrangian, and it is mr squared theta dot squared. That's more or less familiar looking, except for the factor of a half, which is usually there. Plus, now we have a truly familiar looking term, mr squared phi dot squared. Then we have this extremely odd cross term, which multiplies theta dot times phi dot, mr squared theta dot phi dot times cosine of theta minus phi. Then we have to subtract u, so that gives us plus mgr cosine of theta plus cosine of phi. What's that?
Potential energy of the second Bob, but you have to add the two.
Is the energy of both Bob and Hermann being measured from the same reference point?
Yeah. Right. Yeah. No. No, no, no. Yes. Thank you. This one, right? Yeah. That one, yeah. Right. Okay. Now, this is complicated. I'm not going to solve it. What I will do is write down some of the equations of motion, but before I do it, let's work out the conserved quantity. Why is there a conserved quantity? No, sorry, there is not a conserved quantity, because the special direction associated with gravity means that there's no rotational symmetry of this problem. This problem does not have a conserved quantity altogether, which makes it about as complicated as a simple system like this can be. But if we forgot gravity, I don't mean if we forgot it, I mean if we did this way, way out in space where there was no gravitational field, it would still be a rather complicated problem, but it would have a new feature of having a symmetry. This would not be there. Let's get rid of it. And then there would be a symmetry. What would the symmetry be? The symmetry, of course, would be rotation, where you add to each angle exactly the same amount. So it's theta goes to theta plus epsilon, where epsilon is a small angle, and phi goes to phi plus epsilon. Same angle. You can't shift one by one thing and the other one by another thing. You shift them both by the same amount. Remember the last time we defined symmetries so that Q went to Q plus epsilon times F, F of Q. This just means that the F's are both equal to 1. Okay? The F's, which I defined last time, that go along that tell you how a Q changes when you perform the symmetry transformation, in this case, they're both the same. Okay, can we see, in fact, that the Lagrangian doesn't change when you do this? Well, if you add a constant to a theta, if you add a constant to something, you don't change its time derivative. So you don't change the theta dot squared, you don't change the phi dot squared by adding a constant, and you don't change cosine of theta minus phi, because theta minus phi doesn't change at all. So in fact, this Lagrangian has the symmetry. I don't know, would you say we've discovered it or imposed it? I think we discovered it. But of course, we imposed it by getting rid of the gravitational field. So it's a bit of both. All right, let's calculate the angular momentum, or the conserved quantity, the Noether charge, and see what it is which doesn't change with time. If we know that something doesn't change with time, that goes a long way toward helping us solve a problem. It takes a problem involving two variables and really replaces it with a problem with only one variable. Right? It diminishes the number of equations since we know that something doesn't change with time. Okay, so let's see if we can figure it out. The rule is the Noether charge is pi sub I times what I called f sub I, summed over I, where pi sub I is partial of the Lagrangian with respect to q sub I dot. And what about f sub I? In our case, the f's are just 1. So this just becomes pi sub theta plus pi sub phi. Not too surprising. It's just the sum of the canonical momenta of theta and phi. Why? Because the f's are both equal to 1. But now we have to calculate what pi sub theta and pi sub phi are. You might expect that pi theta is just related to theta dot. And you might expect that pi phi is just related to phi dot. But it's more complicated because of this mixed term here. So let's calculate them. Pi sub theta is equal to the derivative of the Lagrangian with respect to theta dot. All right, what is that? It has, here's theta dot over here, m r squared theta dot and a factor of 2. When you differentiate theta dot squared, you get twice theta dot. Partial of L with respect to theta dot has twice m r squared theta dot, but we're not finished. There's this mixed term here. There's a theta dot in it. So there's a plus m r squared phi dot times cosine of theta minus phi. That's pi sub theta. What about pi sub phi? Same game. All right, phi dot looks very similar, the first term, except it doesn't have the 2 in front of it. Because of the half which appears in Lagrangian, instead of the 2 appearing in pi, we just have mr squared phi dot. This is partial of L with respect to phi dot, but then we also have a term from here, plus mr squared. Now it's theta dot times cosine of theta minus phi. Look how odd it's gotten. Pi sub theta involves phi dot, and pi sub phi involves theta dot. So things have gotten a little mixed up. Not to worry, we just nevertheless follow our nose, mechanically add these things together. I won't bother, well, I will write out the answer. The answer is 2mr squared theta dot plus mr squared phi dot. I think I'm missing an mr squared here, right? Plus mr squared theta dot plus phi dot times cosine of theta minus phi. This is the thing which doesn't change with time. We can call it the angular momentum. It's the thing which is conserved because of rotation symmetry, and it doesn't change with time. It gives us a piece of information. If we know the angular momentum at any given time, let's say at the start of the trajectory, then it stays fixed forever after, and allows us to figure out what theta dot is in terms of phi dot. It allows us to eliminate one of the variables of the problem. Okay, only one variable. Allows us to eliminate one thing and simplifies the equations for us. But as you can see, the main reason for doing this was to show you how mechanical it is to calculate the Lagrangian, to calculate the conserved quantity, and then to calculate the equations of motion. Let's do the equations of motion. It's boring. It's quite boring. Anything which has been reduced to being mechanical like this is naturally going to be boring. And that's the goal of physics, to make everything really boring. Okay. Oh, this is not the Lagrangian here. This is the angular momentum. Let's not confuse it with that L up there. Okay, so let's calculate the equations of motion. We've calculated pi. Let's just do theta. I won't do phi. We'll just do theta. The first thing is to calculate d by dt of partial of L with respect to theta dot. Okay? That's already a little bit complicated, but it's straightforward. D by dt of, what is it, 2mr squared theta dot. That's just got theta second derivative, theta double dot. Right? mr squared, they're constants. Then there's plus, what's the other term? Question? I heard somebody say double dot. This is double dot. D by dt of theta dot is theta double dot. Right. All right. But this is not the full pi sub theta. The rest of pi sub theta has this term, so it has another mr squared. Again, mr squared is a constant. Then it has phi dot, and then cosine of theta minus phi. All right, this is a little bit complicated. D by dt of this term just gives us theta double dot. D by dt of this term is a little bit complicated. We have to differentiate phi dot times cosine of theta minus phi. You know how to do that. I'm not going to waste your time. It'll give us a phi double dot term, and then it'll give us a term where the time derivative hits the cosine here. I'll let you do that. Straightforward calculus. It'll give you a few more terms than you might have expected. So on the left side, we have d by dt of a very definite quantity. We can feed this into a computer, calculate phi dot at each instant along a trajectory, differentiate it, and all of this can be worked out easily. And that's equal to what? That's equal to the derivative of the Lagrangian with respect to theta itself. That's equal to dl by d theta That's Lagrange's equations. Where does theta appear? The,
Calculus question with respect to that cosine
okay,
theta minus phi.
yeah.
That's the same whether it's phi minus theta or theta minus
Yes, it is.
phi.
Yes, it is.
But if you use the multiplication rule, doesn't there come in a minus sign? Chain rule on the,
Well, you just follow your nose. Why, yeah, the derivative with respect to one of them is minus the derivative with respect to the other. It's true. Whenever you have a function of a difference of two variables, the derivative with respect to...
saying that since I'm doing it,
Yeah, you'll pick up a minus sign. When you differentiate this with respect to phi, you'll get a minus sign from over here.
yeah, right.
Okay? Yeah. Yeah. Okay. So I assume you know how to do this derivative on the left. On the right, the only place where theta appears is in this cosine here. Okay? So,
The confusion I was having is I forgot that I'm taking a derivative dt,
yeah.
so I actually have to differentiate with the partials of both phi and theta.
Yeah. 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 You'll get one term with a theta dot and another term with a phi dot, and they'll have opposite sign. Right. Okay, so I'll leave that to you. There's nothing terribly interesting, straightforward calculus. And the other thing, which is here, is the right-hand side, which is the derivative of the Lagrangian with respect to theta, and that is just equals mr squared phi dot, and then the derivative of cosine theta, sorry, the derivative of cosine with respect to theta just becomes minus sine of theta minus phi. Can everybody read this? I can't.
You're taking the partial respect to phi theta. I think you want to take the partial respect to Laplacian, so you get a
Laplacian. Laplacian.
Lagrangian.
Yeah.
So you get a upstairs.
Oh,
You got a theta dot t dot.
mr squared phi dot times the derivative.
Keep going. That's not the
Upstairs. How much higher? Oh.
Lagrangian.
Oh, you're right. Thank you. Thank you, thank you, thank you, thank you. Very good. Yes. The derivative of the Lagrangian with respect to theta. So that's going to give me, what, another phi, theta dot?
Yes.
Yeah, thank you. Good. Okay. But it's mechanical. The point is it's mechanical. It's complicated. The final answer is complicated, but mechanical. No ambiguities in the steps. All right. This is the equation of motion for the double pendulum, the theta equation. You can work out the phi equation. In the absence of a gravitational field, it's already complicated. One of them spinning around is exchanging energy back and forth and angular momentum back and forth with the other. It's a rather complicated motion that these things undergo, even in the absence of the gravitational field. But the one thing that you have going for you when there's no gravitational field is you have a conserved quantity that you can use to replace theta dot by its expression in terms of phi dot. You also have energy conservation. Right. Right. That effectively eliminates one whole degree of freedom. And right, you have energy conservation, so you can fix the energy and you can fix the angular momentum. And that is effectively two equations that allow you to eliminate, let's say we can eliminate phi dot and phi out of the equation and just have an equation for theta. All right. But we're not in the business of solving equations here. We're in the business of studying the formal structure of mechanics. And as I said, the main reason for doing this tonight was to show you that a problem which is very, very treacherously tricky when you try to think about it in terms of F equals ma, and it would take us a lot longer to do on the blackboard, you simply set up what you have to do. The rules are figure out the velocity, square it, write 1/2 mv squared, figure out the potential energy, subtract it off, and then you're going. You're on your way. All right, I said I would take a simple problem, the pendulum, then a complicated problem, the double pendulum. We'll come back to the double pendulum when we talk about chaos a little bit. The double pendulum is a very chaotic system, which means it's rather unpredictable, despite the fact that the equations of motion are in some sense exactly predictable. It does some rather unusual and weird motions. We'll come back to it as an example of chaos. But for now, it was just an example of the canonical or the Lagrangian formulation. What is incidentally, what is the energy of the system? Well, all the terms with theta dots are kinetic energy. The term without the theta dots are potential energy. For a system like this, the energy is simply the kinetic energy plus the potential energy instead of minus. So you would just change the sign of this term. I think that's right. So in that sense, it's similar to the ordinary pendulum. All right, the next problem that I want to study is the most basic problem of all of theoretical physics. It's the one that comes up over and over and over again. What is it? The harmonic oscillator. There's one problem which is a little bit simpler than the harmonic oscillator, a little more fundamental, I don't know, fundamental, a little, and it's of course just the free motion of a free particle with no forces on it. That's really boring. The harmonic oscillator is a boring problem, but not quite as boring. By boring, I mean, of course, that the motion is so simple and so completely predictable that it has no surprises. But it does have a structure, a mathematical structure, and which underpins so much of physics that we need to get it right from the beginning. The pendulum is almost a version of the harmonic oscillator. If you look at the pendulum and you displace it just a little bit from the origin, it swings back and forth very, very much like an ordinary harmonic oscillator. If you displace it far from the origin, then it's not quite true. The mathematical connection is as follows. The potential energy minus mgr cosine theta, what does that look like? Let's draw a picture of it. Just minus cosine theta. Cosine of theta looks like this, right? From 0 to 2 pi, swing all the way around. Minus the cosine, which is what's in the potential energy, looks like this. So it's minimum at theta equals 0. In other words, the energy is minimum when it's hanging straight down. Okay? That's the expression for the energy. I could continue it back a little bit to negative values of theta. And it's minimum right here. Any function which is minimized at a point has a basic feature that its first derivative is 0. Right? What comes next is the second derivative. Right? Any function like this, which has a minimum, is well approximated by a parabola at the bottom. In other words, by something proportional to theta squared. This is approximately equal to high precision when theta is small. In fact, to correct the second order in theta, it's equal to mg, well, let's get it straight. It's minus mgr, which is just a constant and not interesting, plus 1/2 mgr theta squared. I'm simply using the fact that near the bottom of the orbit like this, you can approximate this curve by a parabola, something proportional to theta squared. Any function which has a minimum, a smooth minimum like this, typically will be approximated by a parabola. Well, that's not quite true. It could be flatter than a parabola, but that would be an exceptional situation. But typically, when a function has a minimum, at the minimum, you can approximate it by something proportional to theta squared. If you did so, and you ignored the constant in the energy, which is of no particular importance. Did I get this wrong? Did I get the sign right here? Let's see. U is plus. Then we would have in the Lagrangian minus 1/2 mgr theta squared. And in the energy, we would have plus. But the important thing here is that it's just proportional to theta squared. It's a very simple expression, the simplest expression you can imagine for the kinetic energy about a minimum, about a point of minimum energy, something quadratic. That's what defines the harmonic oscillator. When the energy or the potential energy is simply quadratic in the coordinate, that's called a harmonic oscillator. All right, so let's instead of calling the coordinate theta, let's call it x. Here's another system that we might study. An object on a spring with a mass m. The spring has some equilibrium position, some natural length when it's stretched and not under any stress, when it's not stretched or compressed. And if you compress it or you stretch it, the mass will oscillate about the equilibrium point. If we call x equals 0 the equilibrium point, in other words, let's call this the x-axis, and take x equal to 0 at the equilibrium point, then we have to do some work to stretch it, we have to do some work to compress it, and the potential energy is proportional to x squared. The potential energy in this case is proportional to x squared with a constant coefficient k, and it's conventional to put a 2 there. This is called the spring constant. The spring constant, kx squared, and by convention, we put a 2 there. Yeah? I just dropped it because a constant doesn't do anything. But you're right, it's there. But it wouldn't make any difference to anything. The reason is because it's a constant, and the only things which come into equations of motion are derivatives of the Lagrangian, that will not contribute anything to the derivatives of the Lagrangian. So you're right, there is another term here. It's a constant term, and just ignore it because it doesn't affect anything. Okay, so for a simple system like a spring, a good approximation is to say that the potential energy is positive. You increase the energy by stretching the spring. You also increase the energy by compressing the spring. In either direction, you have to work to move the spring. Kx squared divided by 2. The fact that there's a numerical number there, that's not surprising. The 2 is simply a matter of definition. K over 2 is the coefficient in the energy. The Lagrangian is then 1/2 mv squared minus k over 2 x squared. What about the force on the oscillator? What about the force? Remember that force is equal to minus the derivative of potential with respect to x, and that's equal to minus kx. The derivative of this with respect to x is just kx. Force is equal to minus kx. The minus sign means that the force is a restoring force. If you stretch so that x becomes positive, the force is negative, pulls you back. If you compress so that x is negative, the force is positive, and again, it's a restoring force. So this is the Lagrangian. The force being proportional to x has a name. It's called Hooke's law. How do you spell Hooke? H-O-O-K? With it? 2 O's. E. All right, I wasn't sure if there was an E at the end. I didn't remember. Hooke's law. This is Hooke's law. Hooke was Newton's best friend. Okay. So this is your standard spring, mathematically idealized. The real spring, of course, would have a more complicated formula. In fact, if you stretch the real spring enough, it would break. So there's all sorts of complicated nonlinearities in it. This is an idealization, and it's good for small excursions of the spring. No. No, of course not. You can't derive Hooke's law. You can only experimentally measure it. But what you can say is that on mathematical grounds, a function which has a minimum has no first derivative. If it has no first derivative, that means there's no term proportional to x. A constant is irrelevant. We don't care about a constant in the energy. Next, there could be a term proportional to x. But if we're at the minimum, then the derivative of the function with respect to x is 0, and the first order correction, the first order term is 0. The next term is proportional to x squared. In other words, if we expanded a function in a Taylor series expansion in powers of x, the first term could be a constant, which we're not interested in. The next term would be x, proportional to x, but if we're sitting at the minimum, then there's no slope. X would mean a slope. There is no slope, so that's not there. Then there's x squared, and then there's all the higher terms that could be there, constant x cubed, another constant c prime, x to the fourth, and so forth. The point is that if x is, all right, the main assumption, there's also a constant here, let's call it d. I've already used c and c prime. It's conceivable to think of a function which begins with order x cubed. In other words, where the constant multiplying x squared is just plain 0. Right? That would be rather special. It's usually deemed to be a fine-tuning of some sort, that there would be no quadratic term. It's not a fine-tuning to say there's no linear term. It's just a statement that we start at the bottom, wherever the bottom is. That there would be no quadratic term would require some careful tuning of a function. If there's a quadratic term, that's the first thing. Next would be cubic, quartic, and so forth. These terms are not Hooke's law. Right? But the point is that if x is small enough, that if we only deviate a little bit from the origin, then x cubed and x fourth are much, much smaller than x squared. So for small displacements, these terms can typically be ignored, unless the first term is absent. If the x squared term is absent, then you have to begin with x cubed. But if the first term is not absent, then for sufficiently small oscillations, it always begins with order x squared. So in that sense, Hooke's law is derivable, in the sense of an approximation for small oscillations under the circumstances where nobody carefully fine-tuned away the first term here. Hooke's law is very general. This is the reason, this is the fundamental reason that the harmonic oscillator shows up in so many places. It's always there when you're oscillating about the minimum of a potential energy, unless somebody has very carefully fine-tuned away the first order correction, the first order contribution, second order contribution. Yeah. No, 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 no. If there's a term of order c cubed. No, of course not. No. Springs break if you stretch them too much.
Well, so it's not exact at all. It's not as if there's a certain point at which it's not good.
No.
But in an instant,
No.
it actually is.
No,
It's always a
right. It's always an approximation on the one hand, but it becomes a better and better approximation as the oscillations are smaller and smaller. So you imagine studying this very, very small oscillations, it becomes progressively more and more exact. Okay? It becomes a better and better approximation as the oscillations become smaller and smaller. Of course, as the oscillations get smaller and smaller, they get less and less interesting. You can't see them after a point. They're too small. So you have a highly accurate theory of something which is too small to be measurable. The real question is, where does this term come in compared to this? And what is the nature of your experiment? How big are the oscillations? And is this term important relative to this when the oscillations have a certain size? Right? So it becomes a question of estimating the relative importance of x cubed relative to x squared. And that depends on the size of these coefficients. Right? But for almost all systems, for sufficiently small oscillations, in other words, sufficiently small energy, the x squared is usually a good approximation. The linear term, if we put a linear term in, let's put a linear term in, okay? Give me another letter. K? K. Well, I've already used K over here. I don't want to. AX. What would this do? Well, it would put a first derivative over here. It would mean that the function now has a first derivative. And it would look like this. Well, that would just mean that you started at the wrong point. Instead of starting at this point, start at this point. Shift x, shift the definition of x so that x equals 0 at this point, and then there won't be a linear term. Yeah, okay. So the x, the constant coefficient is of no importance, a constant. The linear term can always be shifted by going to the minimum, by starting your coordinates at the minimum. That gets rid of the first term, and then you're left with the x squared term. Right. All right, so as I said, in that sense, it's a rather general structure which is always a good approximation for sufficiently small oscillations. It always breaks down when the oscillations get big enough, whatever they are, whether they are light oscillations, sound oscillations, water waves, springs vibrating. For very small oscillations, Hooke's law is a good approximation. For large oscillations, it breaks down. The pendulum is a perfectly good example. What comes after theta squared if you expand cosine theta? Theta to the fourth. There's a theta. It happens there's no theta cubed term. There's a theta to the fourth term. So if you take large swings, the large swings are sensitive to the higher terms in the cosine. But for small enough swings, only the theta squared term is important. All right, yeah.
In that equation,
This one?
no, above. Shouldn't that sign be minus?
I've lost track of it. Let's see.
Because it's minus u, right?
You are right. Yeah. Yeah. I think you're right. Yeah, sounds right.
No,
No?
you were right the first time.
I was?
You had the minus sign, so t minus u changes it to plus.
Yeah, but cosine has 1 minus theta squared over 2.
You put the plus in when you were talking about changing it to a Hamiltonian.
Yeah,
Oh,
right. Yeah. No, I think it's minus. Measured from theta equals 0, the potential energy is positive. If the potential energy is positive, then in the Lagrangian it should be negative. All right, the importance of this system, I've explained why it's important, why it recurs over and over in physics. Now we have to understand it. We have to study its properties, its Hamiltonian, its Lagrangian, its equations of motion, and all the things that we've learned up till now, apply them to this system. Yeah.
So just to follow up on your
Say it again.
rationale to why this is important, you say that if the motion is near the minimum of the energy,
In other words, if the system is disturbed only a little bit.
so then this approximation will become important.
Yeah.
On the other hand, mathematically, you still have to worry about it as time goes on. You don't get a situation that you get out of that range. So
Yeah.
how do you guarantee that?
Yeah. For the simple one-dimensional system, or systems more generally than that, It's energy conservation which prevents the oscillations from getting too big. You have only a certain amount of energy. Let's write down the energy. The energy, H, is m over 2 x dot squared plus k over 2 x squared. All right? A large excursion, a large x, will mean a lot of energy. If you only have a small amount of energy, this simply can't get too big because it's positive. If it was negative, if you studied a system with a negative term in the potential energy, then x dot can get big and x can get big and cancel each other and keep the energy bounded. It's because both these terms are positive, x dot squared and x squared, neither one of them can get big if the initial energy is small. So that's a very good question. And there's a very good answer, energy conservation. Right. It wouldn't work if the potential was upside down. Potential being upside down means you're standing at the top of a hill. If you displace the thing a little bit, it'll go flying off the hill, and your approximation of a small oscillation will not be consistent. All right. All right, so this is a system worth exploring since it comes up so much. Here it is. I'll write it over again. Let's work out its equation of motion. We could, of course, just write F equals ma for this case. I mean, for this case, it's simple enough. We can just write F equals ma. But let's not do it that way. dl by dx dot, that's pi sub x. dl by dx dot is just mx dot, just the ordinary momentum. d by dt of that, that's derivative of the Lagrangian. That's d by dt of dl by dx dot. That's the left-hand side of Lagrange's equations. The right-hand side is just dl by dx. That's this. So that's minus k over 2 times 2x. This, of course, is just good old F equals ma. Mx double dot is equal to minus kx. Hooke's law. It's nice to divide by the mass. Let's divide by the mass here. Notice the only thing which comes into the motion is the combination k over m. K over m is the important quantity. If I were to change k and change m, keeping k over m fixed, the equation of motion would not change. All right, this is an equation whose solution is well known. Everybody know what it is? Anybody not know what it is? It's cosines and sines, corresponding to just an oscillation. Why is it cosines and sines? Supposing I take a function like cosine of t, and I differentiate it once. Then I get sine. What happens if what do I get if I differentiate cosine? Minus sine. And then if I differentiate again? Minus cosine. So the second derivative of a cosine is proportional to itself, but with a minus sign. Now, let's not, cosine t is not quite right. Cosine omega t is a better bet, where omega is the angular frequency. Just a number, okay? It tells you how fast the oscillation is oscillating. Omega, the bigger omega is, the faster the oscillation. This is the angle, this is just called the frequency of the oscillation. What is the first derivative of this with respect to time? Again? Minus omega sine omega t. What's the second derivative? Minus omega squared cosine omega t. So if I call this x, then this is x double dot, and notice that it's just minus omega squared times x. That's what this equation says. It says the second time derivative is proportional to x itself with a coefficient k over m. Same minus sign, and so we identify that the frequency of the oscillator is k over m, or frequency squared. Omega squared equals k over m. Or omega, the frequency, is square root of k over m. Supposing instead of putting cosine there, I put sine. Same thing. If I differentiate sine, I get cosine. If I differentiate cosine again, I get minus the sine. So this would also work for sine. In fact, it will work for any combination, any linear combination. X is equal to a times cosine omega t plus b times sine omega t. Any function of this form will satisfy this equation if omega is equal to the square root of k over m. You can check that. Each one separately does, and if you add them together, they do. Why are there two coefficients? Why are there two? Any a and b will work. Why are there two coefficients in the solution? Right. It's because you have to specify two things to start a solution out. One way of saying it is you have to specify a position and a velocity. So there are two parameters that govern a solution. There have to be, in every solution of a simple equation, second order equation, there have to be two constants for each one of the coordinates. Okay, the general solution. One to fix the initial condition, the initial position, and the other to fix the initial velocity. You can work out a and b if you know the initial position and the initial velocity. So this is all the solutions there are. There are no other solutions beyond this. There's another way to write it. You can also write it as x is equal to a times cosine of omega times t minus t naught, where t naught is just some constant starting time. Again, it has two parameters. An amplitude, let's call it capital A, an amplitude of oscillation, which tells you how big the oscillations are, and a particular time, which is the time when the oscillation reaches its maximum. In other words, you can either write the general solution in this form with two coefficients a and b, or in this form with a coefficient that's called the amplitude, and this one is called the phase. In this form, t naught is the time at which the oscillation reaches its maximum. All right. So, or if you like, the starting point, if you imagine stretching the spring and letting it go, stretching it to a maximum and letting it go, the time that you let it go is this t naught over here. When t is equal to t naught, the cosine is at its maximum value. So these are the two forms that the general solution takes. And it's perfectly obvious why it's called a harmonic oscillator. Well, I don't know why it's called harmonic, but it's called an oscillator because it oscillates, it vibrates. It vibrates with a cosine of omega t. All right, that of course is no doubt familiar to most of you. Say it again. The phase is t0. Yeah. Right. So it's two parameter family of solutions, which, as I said, you can either take to be. The theorem, of course, is that if you add a sine and a cosine like this, it's always equal to a cosine of a shifted argument. All right, that's the basic setup for the harmonic oscillator. But now we want to think about its Hamiltonian first, and its canonical momenta, canonical momentum. First of all, is P, which is the same as pi sub x, which is the same as the derivative of the Lagrangian with respect to x dot. And what is it? It's just mx dot. It's just good old momentum. Nothing surprising there. After all, it is just a particle on the end of a spring. So that's P. P or pi. How about the Hamiltonian? Let's work out the Hamiltonian. The Hamiltonian is px dot, it's our usual thing, canonical momentum times velocity, minus the Lagrangian, minus L. And that's, let's see, P is mx dot. So px dot is mx dot squared, twice the kinetic energy, but now minus the Lagrangian. So minus m over 2 x dot squared plus k over 2 x squared. In the Hamiltonian, the kx squared term has the opposite sign as it had in the Lagrangian. Okay. So this is exactly what you would expect. mx dot squared over 2 plus k over 2 x squared. And it's conserved for all the reasons that we worked out last time. Right. We worked out that this quantity is generally conserved. So this is the conservation of energy. This is the energy. But we can write it in another form. And now I'm going to start to teach you about the Hamiltonian formulation of classical mechanics. Up till now, we've dealt with the Lagrangian form of the equations. We want to pass now to the Hamiltonian form. The Hamiltonian form works not with x's and x dots or q's and q dots, but it works with the basic variables being canonical momentum and coordinates, q's and pi's, or q's and p's. Why? Why are we doing such a thing? I have to admit, I have no idea why Hamilton started thinking about things that way. The ultimate reasons boil down to quantum mechanics. We're not doing quantum mechanics now. We're going to do some things which may mystify you a little bit. You'll start to get familiar with them. They're very pretty, they're elegant, they're simple. But what the motivation that Hamilton had for going along this route is quite mysterious. I don't know what it was. Nevertheless, Hamilton said the important quantities, well, we'll come to see why it's so important as we go along. But Hamilton said he wants to work not with the quantities q and q dot, but rather with q and p. He saw some sort of symmetry between q's and p's. He saw something very special about the canonical momenta that's not apparent until you start to work with it. I will tell you what it is as we go along, but the goal is to rewrite mechanics, not in terms of positions and velocities, but in terms of positions and canonical momenta. This may be, at this point, this is probably a mystery to you, why one would want to do that. And it really didn't achieve its full importance until quantum mechanics. So at this point, you have to hold off and say, okay, he's doing some magical, mystical mumbo-jumbo with p's and q's instead of q's and q dots. I don't know why, but we'll start to see as we go along that it has some... the form of the equations is especially simple. It's especially simple in terms of p's and q's.
But he did some other stuff like that in mathematics.
Yeah, that's right. Yeah. Some people think he foresaw quantum mechanics. I don't think he foresaw quantum mechanics. He just...
Is there not also significance of the harmonic oscillator in quantum mechanical thing, atoms, and is that something you can kind of think that?
Say it again.
Isn't there significance of the harmonic oscillator in terms of quantum mechanics of atoms?
Certainly.
And is that something you
Well, again, any system when disturbed a little bit from equilibrium will behave like an oscillator. So a molecule, I'm not sure exactly what question you're asking. The reason that we study oscillators is because small deviations from equilibrium oscillate. The reason is the same in quantum mechanics as in classical mechanics, but there's a feature in quantum mechanics which isn't there in classical mechanics. There's zero-point energy. It's impossible to lower the energy to an arbitrarily small amount. So the idea of an arbitrarily small oscillation is not sensible in quantum mechanics. That means that there is no real limit in which the oscillator becomes perfectly accurate. But I didn't want to get in that now. I want to keep away from quantum mechanics until we study quantum mechanics. Let's move on. Let's write the Hamiltonian in terms of p's and q's instead of q's and q dots. Here it is. Here's the Hamiltonian, or the energy. There's the expression for the energy. Here's the expression for the canonical momentum. P is mx dot. To write the Hamiltonian in the form that Hamilton would have wanted you to write it in, he would want you to get rid of all the x dots and replace them by p's. In each case, the p's will be functions of x dots and x's. In principle, you can solve for the x dots. We'll work out some examples. You can solve for the x dots and write them in terms of p. For example, in this case, it's very easy. X dot is just p over m. So let's write that down. X dot is p over... Yeah, we're going to get that. Well, not really. All right, so this equation here tells us that x dot is equal to p over m. The momentum divided by the mass is the velocity. Let's plug that into here. This now reads then p squared over 2m. Why is it over 2m? X dot squared will be p squared over m squared. So when I write x dot squared, I will have two m's in the denominator. Two m's in the denominator, one m in the numerator. It'll be p squared divided by 2m. So whereas when you write the energy in terms of velocities, the m appears in the numerator, when you write it in terms of momentum, the mass appears in the denominator. Big deal. But keep it in mind that it's a useful mnemonic. Whenever you see something multiplying an x dot squared in a Lagrangian, it usually winds up, that thing gets into the denominator in the Hamiltonian. Plus kx squared over 2. Now notice there's a kind of symmetry in this problem between p's and x, between p and x. Apart from the coefficients k and m, the Hamiltonian is perfectly symmetric between x's and p's. It's of the form, roughly speaking, of x squared plus p squared. Well, not exactly. It has some coefficients. Something times p squared plus something times x squared. It has a very nice symmetry between p's and x's. And that symmetry is one that we'll exploit over and over again, that the equations of Hamiltonian mechanics are entirely symmetric with respect to x's and p's. They look the same if you interchange x's. Not exactly, but the structure of the equations is symmetric between x and p's. But for now, just recognize that the energy has p squared plus x squared. Well, not quite. 1 over 2m times p squared plus k over 2 times x squared. Let's make a diagram representing on the horizontal axis x and on the vertical axis p. Now you could have used velocity on the vertical axis, After all, velocity and momentum are proportional to each other. But we're going to use momentum now, for now. Momentum in the vertical axis, horizontal axis is x. How? Yeah. A starting point for the motion consists of a value of x and a value of p, a position and a momentum. So if I tell you the position and the momentum at the start of the motion, that corresponds to a point on the xp plane. Incidentally, the xp plane has a name. It's called phase space. And it has a symmetry between x's and p's that it would not have if you used velocities on the vertical axis. But that's something that will come with time. You start the system out. It starts with a velocity and a position. You can translate the velocity into a momentum just by dividing by the mass. And so the starting point is some point in phase space. What happens next? The system starts to move. It changes both its x's and its p's. In this case, there's only one x and one p. The velocity changes, the position changes. The system moves in the phase space. How does it move in the phase space? Can we track its trajectory as it moves through phase space? Well, first of all, we know that energy is conserved. That means that p squared over 2m plus k over 2x squared, which is equal to the energy, call it the Hamiltonian or the energy, same thing. Sometimes I'll call it energy, sometimes I'll call it Hamiltonian. We tend to call it Hamiltonian when we're talking about its functional form in terms of x and p. We tend to call it energy when we're just thinking about the numerical value of the energy. The numerical value of the energy is conserved with time. It doesn't change. And so that tells us something about the motion. Can you see from this what kind of motion it has? Okay, it would be a circle if m and k were both equal to 1. Then it would be p squared plus x squared is equal to 2e or something. Okay? Not quite a circle. If you put some coefficients in here, coefficient p squared plus another coefficient times x squared is equal to a constant, then it's not quite a circle. What is it? An ellipse. So the motion in the phase space is elliptical. It's not a very good ellipse, is it? Okay. Let's figure out the intercepts first of all. If it were a circle, in other words, if m and k were adjusted so that the coefficients here were the same, then the radius of the circle would be controlled by e. In fact, e would be the square of the radius, right? Roughly speaking. P squared plus x squared is equal to twice e. Twice e would be the square of the radius. So if we change the energy, that will change the orbit by changing its radius. Now, the ellipses are all of the same exact shape. They would be circles if k and m were 1, all right? But they have different distance from the origin. They have different radii. Okay? Same shape, same eccentricity, different radius, different overall radius, and the radius is controlled by the energy. So if we start the system someplace, there's an ellipse passing through that point. We take that ellipse, and the system will just continue to move on that ellipse. Let's find out where it intersects the x-axis and the p-axis. It intersects the x-axis at the point where p is 0. Where p is 0, x, let's work it out, x, where p is equal to 0, put it up here, k over 2 x squared is equal to e, or x is equal to the square root of e divided by twice e divided by k, I believe. Twice e divided by k. Do I have that right? Yeah. Okay, so the x-intercept here is square root of 2e over k. Notice that as e gets bigger and bigger, the intercept moves out. What about the y, or the p-intercept here? The p-intercept, you do the same thing. The p-intercept is where x is equal to 0, and we just solve for p divided by 2m is equal to e, and that's p is equal to the square root of 2me. Square root of 2me. So the x-intercept is 2e over k, or the square root of 2e over k. The y, or the p-intercept, is 2me, square root of that. So if we know the energy, and we know the mass, and we know the spring constant, we can start drawing these ellipses in phase space. And wherever we start, the system just moves around on the ellipse. Incidentally, by squeezing the x-axis and expand, or by an appropriate redefinition of x and p, we can turn these into circles easily enough. Okay? We can easily turn them into circles by rescaling either the x-axis or the p-axis, squeeze the x-axis a little bit, or expand the p-axis, or some combination, and you turn them into circles. I won't do that. Just leave it the way it is. But you can think in your head of circles. Circles in phase space, or ellipses in phase space that can be rescaled to circles. Now, how long does it take for the phase point to go all the ways around? That depends on the frequency of the oscillator, omega. The larger omega, the shorter the amount of time for it to go all the ways around. All right, so the phase point moves on ellipses. It moves around in a time which doesn't depend on where you begin. So in other words, if you actually thought of circles, think of circles, then the whole phase space rotates around with frequency omega. Every point, no matter where you begin, it takes exactly the same amount of time to go around. And so wherever you start in this phase space, you just progress around with the same angular frequency, round and around and around wherever you start. Okay. Supposing you project the motion onto the x-axis. In other words, you don't look at p, you just look at what x is at any given instant of time. How does it move? Well, that's just projecting onto the x-axis, and it just moves back and forth. It oscillates. The oscillator oscillates. And it oscillates with exactly this kind of motion. It also oscillates if you projected it onto the p-axis. All right? And notice when it's furthest out in x, it's moving fastest. No. When it's furthest out in x, when it's furthest out in x, it's moving slowest. Why? When it's way out here at maximum x, p is equal to 0. When it's up at its maximum, x is equal to 0. So when the oscillator is far out, it's moving slow. When it's close in, it's moving fast. And you can think of the two motions, the x motion and the p motion, as the projection of the circular phase space motion onto the x-axis and onto the p-axis. Phase space is quite fundamental. Notice some other things. Now, not all systems move on circles, but all systems do move on surfaces of constant energy. So when you write the energy, however you have to write it, in terms of x and p, then the trajectories in that XP space are surfaces of constant energy. They're contours of constant energy, of total energy. The energy being expressed in terms of X and P. There's another fact that's obvious for this system. Well, if you think about it in terms of circles, it's obvious for this system, but it's also very general. It's going to play a very, very big role in the structure of mechanics. It's the following fact. Supposing you take a little patch of area in the phase space. This patch could stand for your uncertainty in the knowledge of where you begin. You know that you begin somewhere in here, and that's all you know. What happens to it? It just moves around and around and around, but the most important thing is that it preserves its area. Area in phase space is preserved with time. I'm going to come back to that. I'm reaching, I've reached 9 o'clock, and that's the end of my energy, so my Hamiltonian has run out, but yeah.
Last week you talked about the requirement of Lagrangian to have single value velocities for any given dimension.
Yeah, right. We need to be able to solve, where's our equation? We need to be able to solve for x dots in terms of p in order, if our goal is to write things in terms of p and x, all right? If that's our goal, and we will see that it will be our goal, but if that's our goal to rewrite mechanics in terms of x's and p's, we've got to eliminate the x dots out of the problem. That means we've got to solve for the x dots in terms of the p's and plug back in. We can't do that unless x. That would present some problems. Those Lagrangians are deemed to be fundamentally sick, and the sickness. I'll tell you what, we'll do an example or two. Remind me next week. I'll work out an example, and you'll see what goes wrong at the place where you can't solve the equations for something happens. Something happens that's bad. The motion doesn't make sense.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.